Hey, hello, good morning, guys, and this is Coding with Gautam, and today we will be using OpenCV and NumPy to create a software that detects objects using your device camera, or you can link it with another camera. So this is part one. So today it's just going to be the first half, then it's just going to be the mechanics, and then tomorrow we go in depth on what softwares we're using, how all this comes together, non-maximum suppression, and all of this we'll cover tomorrow. So what do we do first? We import Cv2. This line imports the OpenCV library, which provides functions for computer vision and tasks like image processing, object detection, and video capture. Then we import, and so basically this is used to access our camera. Then we have NumPy. So this line imports the NumPy library, NP, which provides tools we can use for arrays and matrices. As you can see, we have to work with these when we're coming down here. So how does this work? So this is landing code. It's basically talking about how to land a rocket, and the target we're using here is a red and white circles interchanging, like a normal target. So we're talking about this one. So it's going to detect that. So then load the YOLO model. So basically the YOLO is an object detection you only look once, is a deep learning architecture for real-time object detections. So you can check that out. So we can see this one, YOLO object detection. So basically it uses comparison. It basically can identify what can happen. We're using a pre-used model. Looks like basically does that in the truck, bicycle, and dog. It will be able to do that. So this is why we're using this to help identify a target. So then we use dnn.readNet. This line uses OpenCV's deep learning functions to read YOLO model weights. So basically the weights of the neural network of how to identify. And in my last video of Emotion AI, in my last video, I talk all about neural networks and weights. So check that out. And then we use a configuration file, YOLO.cfg. These files contain the trained parameters of the neural network that perform object detection. Then the class names. This block loads the class names associated with the YOLO model with open Coco names R as F. This line opens the text file coco.names in read mode R. This file will contain class names, one per line, corresponding to the object categories such as person, car, bike. Then we do classes equals line.strip for line in, f.readLines. This line arrays to each line in the open file, removes any or trailing white space using strip, and then adds the class names to the named classes. Then we use bounding box colors, like here. So basically this line generates random colors for each class that will be used to draw on bounding boxes like we've seen before. So basically the software will use random colors. So you can see truck is green, bicycle is red, and dog is yellow. That's what will be happening. Then so it uses NumPy's random number generation, np.random.uniform, to create an array named colors. This array has dimensions, len, classes, meaning it will have one row for each class, and then 3 columns of RGB color values. Each row is filled with a random number between 0 to 255. This creates infinitely random colors. Then the thresholds of the model. So these lines define 2 important thresholds using object detection. Confidence threshold is 0.5. This variable sets the minimum confidence score required for detection. So basically we're saying that it counts as detected if it's more than 50%. So any detection with the confidence score below this threshold, less than 50%, it won't be discarded. So if it identifies what if it identifies a chair in the background, but it's only 20% sure, then it discards it. Then the NMS threshold, this variable sets the threshold for non-maximum suppression, and NMS will talk all about it. We'll go in depth to NMS tomorrow, but the brief overview is that NMS is a technique used to remove redundant rebounding boxes that might overlap due to slight variation. A higher threshold means stricter NMS. So basically, instead of if we have just like many pieces of grass, instead of identifying one, it may have many boxes, and we're using 0.4 to identify that we need to be strict about where we put our boxes. So then, opening the webcam. So this is the line that does it all. This line opens the default webcam index using OpenCV's video capture functionality. The captured frames will be used for real-time object detection. So let's go into the main loop. This is the main loop of the program. We start with while true. This line reads the frame image from the webcam using cap.read method. It returns a tuple retaining 2 elements. Ret is a boolean. So basically, ret is a boolean, and then the frame is whether the frame is present or not. And then, if not ret, so basically it checks if the frame was successfully captured by using the ret value returned. If ret is false, meaning that you could not capture the frame, that the thing didn't turn on, that we weren't able, that the webcam was able to efficiently capture any data, then it says failed to capture, and then it retries trying to open the webcam. Then resizing the frame. So it resizes the frame for faster processing, height, width, channels, and frame shape. Resize frame, cv2.resize, frame 416, interpolation, cv2.interlinear. So this block resizes the captured frame for faster processing by the YOLO model. So here's what happens. We have the height, width, and channels is frame shape. This line extracts the height, width, and number of channels, usually 3 for our red, green, and blue, and then the original frame shape. Then we use resized frame. This line uses the frame of the new size, 416, pixels from using Cv2's resize function, and then the interpolation parameter is set to interlinear for smoother interpolation. Interpolation is basically the grouping. Then we create a blob for the 4D image. So blob is cv2.d and then blob from image, resize frame 0.0392, 416, 3 zeros true, and crop is false. So this line creates a 4D blob from the resize frame. Blobs are a specific data format that have been used for feeding images into deep learning models. This code snippet performs the following. So this function takes the resized frame at a scaling factor of 0.0392 that just works best after running many variations, and the target image size 416, a value subtract from each channel. You set 0 to each channels, so because RGB. Then a boolean indicating normalization set to true, and a cropping flag is set to false. Then it converts the image data into a 4D blob suitable for the YOLO model. Then you set YOLO input. Then you net set input. This line basically created blob as the input for the YOLO model. This model will process the input to generate object detections. Then this line retrieves the names of the output layer of the YOLO model. These zeros will contain detection information. So then, this is it for today. Just getting everything set up, understanding how we're using Cv2 and YOLO. Tomorrow we dive in deep into how the image detection works, how we use non-maximum compression, and how we do all the math and using arrays and matrices using NumPy. So thank you guys for watching. Don't forget to like and subscribe, and keep following for the rest of the series.